right, so what we're going to talk today about is something that's a little bit fun, I think. Hopefully you'll think so too, is volumes of revolution. So what we're going to do is we're going to take the areas we found, right, when we did upper minus lower to find the area between two curves. We're going to take the area between two curves and we're going to revolve it around an axis of revolution. Okay, and I have my Geometry Sketchpad program here that'll show us this area, which is under the square root function. And we're going to take a rectangular area, and we're going to revolve it. Okay, so let's see what happens when we revolve one rectangle. There it is, it's revolving. We can go, ooh, ah, right? There we go. So it revolved, yes? But that's only one rectangle. But what shape is it? Well, it's a cylinder, that's right. Brilliant observation. It's a cylinder. Well, it's a cylinder that's vertically shaped. And for those that are on the video, aren't going to be able to see me writing this on the board, but cylinders have volume, don't they? I mean, they do. What is the volume of a cylinder? Pi r squared h. You're right. It's pi r squared h. And in this case, r is what? It's the function height, isn't it? Do you agree that r is the function height? So r equals f of x in this case, and h. Well, h is the height, which in this case is the change in x here. Would you agree that the h is the change in x? It is the change in x. So we can have volume equaling pi f of x quantity squared times the change in x. All right, but that's only one cylinder. Let's show all the cylinders. We're going to see all of them. Here we go. And you see how I have only 5 of them, but if I were to increase the number of cylinders, what happens? It gets better and better, right? The approximation. And the approximation gets better and better to the point where it's the actual volume, right? Well, in AP Calculus, we don't call these cylinders, we call them discs. And there was some discussion yesterday about how we spell disc.
D-I-S-K.
Yes. D-I-S-K. But some people like to spell them D-I-S-C. In math, can we agree to spell it D-I-S-K? So what happens if I change the number of these? Of course, let's do 10. Shall we do 10? Okay, there we go. We'll do 10. And I'm going to revolve one of them. And if I revolve, see how it's smaller? Sure, the disc is smaller. And then if I see all of them. And we're getting more and more accurate with the volume. So what is it creating? It's kind of creating, somebody said yesterday, a wedding cake. Right? If you turn your head like 90 degrees, you can see the cake. I like to think of this as a jet engine shape. Right? Of course, my husband works at the airport, so I'm a little bit biased in my shape construction there. But it's solid. I mean, it is solid. It's rock solid, right? There's no engine on the inside of it because it's solid, right? So how would I find the volume? I would just add up all the discs, right? Well, what we're going to do today is add up infinitely many of them and get the exact volume of revolution, which is pretty exciting. But what happens if I decide to change, I'm going to reset, the axis of revolution to where the area is not sitting, because the area was adjacent to completely the axis of revolution a second ago, wasn't it? What's happened now? I've got some space here between the axis of revolution and the area, and let's see what happens when we revolve one rectangle now. Well, obviously it's a bigger shape, but what's different? It's a donut, right? I've got a big hole in the middle, right? And let's see them all. Let's see the program do them all. There we go. And do you see how there is a hole right through the middle? It's like there's a bore I've got a cylinder in the middle. Yes? Okay, well, we call this, instead of a disc, because a disc is solid, a right circular cylinder, we call this a washer, because when you're building things and you have screws and washers, nuts and bolts and all of that, right? This is a washer because it has a circular outside and then you have the inside taken out of the middle. Okay, so if your area is not completely adjacent to the axis of rotation, instead of a disc, you're going to have a washer. Okay, so I just wanted to show the visual of what we're doing. So we're adding up a bunch of discs or we're adding up a bunch of washers, okay? And we'll do a bunch of examples of doing that today. All right, so here we go. Let's talk about the math. Okay, so I have the disc method with the disc with a K. And what are we going to do? We're going to revolve around an axis of rotation. Now this is my kindergarten drawing. You always show your axis of rotation by showing an arrow. Now, somebody asked yesterday as well, does it matter if the arrow goes this direction or the other direction? No, because we're revolving it around to create the volume. And then you see that when you revolve the rectangle, you're going to get a disc, right? And the height here, which is the radius, and then the width is going to be delta x here, typically, and then the radius is your function value. Okay? So what would the volume be? Well, the volume, as we mentioned, was pi r squared h. Pi r squared h, and r we said was the function height. So one slice would be the change, we're going to have a change in volume. One slice, we're going to do is delta v is equal to pi times, well, what did we say r was? It's okay to speak, right? Even though we're recording. F of x. So this would be f of x quantity squared, and we said that h was delta x. And that's just one slice of volume, one disc. But we aren't on a mission to find the volume of one disc. We're on a mission to find all of them. Now I could take the limit as the number of discs go to infinity, or there's another representation for that. It's called the integral, right? Using the Roman S, I could say the volume is, the complete volume is going to be pi times f of x quantity squared. And instead of having a delta x, I'm going to change that to an infinitesimally small change in x and make that dx. And before we get carried away, and then we're going to go from A to B, whatever our restraints are. But before we get worried about this is nothing more than pi r squared h, isn't it? Now what is pi? Pi is a constant, isn't it? So I don't usually keep it this way. I usually write this as pi on the outside times the integral from a to b of f of x dx. F of x quantity squared, sorry. Okay, now that's if I'm revolving about a horizontal line. What happens if we're going to revolve around a vertical line? What happens to the disc? It lays flat, like the representation that I have right here on the right. And instead of a dx, I have a delta y, right? And then this radius here now turns into f of y. All right? So let's go down the page here and show our representation here with my colored pencils. Long ago, right? I had fun with that. All right, so do we see how this is a disc? I'm taking this rectangle and I'm revolving it around the y-axis now, and you see I have my indication of direction here. And the width of your disc is delta y, and the radius is now f of y. So how would I write that? I would write that as the volume equals pi times the integral from. Now, with y's, I like to change it from a to b to from c to d, just to make sure that it's a little bit different, right? And then this would be f of y quantity squared dy. The good news is, and we're not going to panic, because we're not going to revolve any areas about any lines that are not horizontal or vertical. Because if we were to revolve them around lines that had a different slope, that would be, monumentally difficult, and it's not beyond the scope of this class. You would do it in a different class, isn't it nice? Not even multivariable does that. Hallelujah, right? Okay. So what happens then if I have some space between my area that I'm revolving and the axis of rotation? Yeah, we're going to have to subtract. But I'm going to draw here. Let's say this is the upper function, right? And then this would be I'll make g my lower function here, right? And we're going to go from a to b here. Do you see how it's a washer? Because I'm revolving the area behind this that we can't see. Around the or the axis of symmetry, okay? Or axis of revolution. Okay, so what we're going to do is we know how to do the disk. So do I know what this radius is? From the upper function to the axis of rotation, that's r, isn't it? Yes? Okay, and this would be having its own radius. We're going to call it little r. So what we're going to do is we're going to find the volume of the big disk and subtract out the volume of the little disk, okay? And the axis of revolution that I have here, let's say that this is y equals 0 to simplify things, okay? So I'm going to say we're going to take the volume of the big disk minus the volume of the little disk, and we're going to subtract them. So we're going to go the pi on the outside of both, right, times the integral from a to b. So what's the volume of the big disk? It's pi r squared h, but its r is f of x dx, yep, minus pi times the integral from a to b of, well, what is little r? Or the little r is equal to g. So this would, I'll put a square here. I'm so sorry, I got to put a square. G of x quantity squared dx. So I have pi r squared h. This is pi r squared h for the big disk, and then I have a pi, oh, this is big r squared, I'm sorry, pi little r squared h for the little disk. And I'm subtracting the little disk out of the middle of the big disk. All right. Now, most people don't leave this as two integrals because you see things that are common in both integrals. The pi's, what else? From a to b and the dx. And using the properties of integrals, can we condense that and make it one integral? So, yep, for the record, everyone was shaking their head yes. Anyway, this is from a to b of f of x quantity squared minus g of x quantity squared, all times dx. And I like to think of this as big R squared minus little r squared. Okay. And this is the volume of a washer. And clearly this is revolved about the x-axis, right? What if I'm revolving it about the y-axis? Yep, it would be. So what would the volume of a washer would be? Yes, you can extrapolate with me. I like that. It's going to be pi times the integral from, instead of a to b, c to d of f of y quantity squared minus g of y quantity squared dy. And we have to have an integral full of y's. And, you know, the limits of integration now are c to d, which is what y is going from and to, versus, you know, x is from and to. So this one is revolved about the y-axis. Okay, so we're going to be finding volumes of revolution with disks and washers. Okay, so let's see what we got. I got 15 minutes. I got to hurry up here. Okay, so find the volume of the solid formed by revolving the region bounded by y equals x, y equals 0, x equals 1, and x equals 0 about the x-axis. So my axis of revolution is going to be the x-axis here. So I show that. So this is clearly the line. I already drew it for you. Y equals x. Or maybe I didn't. But y equals x. And I'm revolving the area bounded by y equals x, y equals 0. What is that in fancy language? Y equals 0 is just the x-axis. So this and x equal 1. They're giving me the upper limit of integration, basically. So this is x equal 1, and then x equals 0. So what is the area between all three of those curves? Well, it's just this yellow area, right? And I'm revolving it about the x-axis. So my rectangle of area is going to be oriented in the dx direction. And since my volume or my area is adjacent to the axis of rotation, what kind of shape do we have? We have a disk. We do. So this is a disk. It's a disk. So how do we set up the integral? D equals pi times the integral from, well, what is x going from and to? 0 to 1 of, well, okay, I like to also say, well, what is r? That's r, isn't it? It's just x, isn't it? So it's pi r squared h, so this is going to be x squared dx. So volume equals pi times, what is the antiderivative of x squared? I'm sorry, it's what? X cubed over 3. Evaluated between 0 and 1. And we get pi times, let's use the fundamental theorem of calculus here, we get 1/3 minus 0, which is just pi over 3 units cubed, because we've moved up from area to volume, so it's 3 on the cube there. Okay? Now, for your viewing pleasure, on the bottom of this problem, I actually used the geometry sketch pad to create what it looks like when we actually rotate it. So I like to give visual images here. What shape is that? What? It's a cone. Wow, cone. It's a cone of radius what? Well, the cone with the radius, we always choose it from the base, don't we? So it's going from 0 to 1, and this is 1. So the radius is 1, and the height is, this is the height, it's 1. And so from geometry, oh my goodness, from geometry, we're rolling back the tape a long way, I know, right? What's the formula for the volume of a cone? 1/3 pi r squared h. So what happens when we go r equals 1 and h equals 1? Pi over 3 units cubed. Wow. Did we just verify the geometric formula for a cone? Pretty amazing? No? Pretty exciting? And for those of you who are viewing this video later, we hear Mr. Johnson in the next room. Don't you? He's I don't even know what he's saying. What's he saying? Is he saying 0? No, it's not even 0. It's something else. He's very excited though. So all of us are a little distracted, but we'll keep moving. All right, so here we go. We're going to find the volume of the solid formed by revolving the region bounded by the graphs. Y equals the square root of x, and x squared about the x-axis. So my axis of rotation is the x-axis. And I've got the graphs here for you. So which one is x squared, and which one is the square root of x? The bottom one is, yeah. So this is y equals x squared, and then we have y equals the square root of x. And the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and x squared about the x-axis. So which area are we talking about? Most people describe this as the body of the fish part. Maybe. So we have to decide whether we have a disc or a washer. What are you thinking? It is a washer. You are correct. So here I'm terrible at drawing washers. So before we even start, I'm just going to tell you it's going to be brutal. Although that has to be, I have to say, that's almost the best washer that I've ever drawn. Pressure, right? Pressure washer. Nice. That's pretty good. Almost looks like a tire too, but that's a washer. So what do we need when we have a washer? We need big R and little r. So I like to, on my sketch, physically draw. What is big R? Well, big R is x squared. Oh, no. Well, no. I'm sorry. It's big R is, it's square root. It looks like it could have been x squared. I get that, but okay. I almost went with you. Okay, what's little r? That's going to be this distance here, which is just x squared. Yep. And so the formula for a washer is pi times the integral from 0 to 1. We're still going from 0 to 1 here. Of big R squared, which is, right, so I'm just going to put root x quantity squared minus little r squared, which is x squared dx. And on the AP exam, you don't even have to simplify that. You get full credit for the integrand here. But we have to simplify it in order to integrate it, right? I mean, all right, so let's simplify it. We get what? Pi times the integral from 0 to 1 of, yes, hallelujah, x minus x to the 4th dx. So what is the antiderivative of that? Good, x squared over 2 minus x to the 5th over 5, evaluated from 0 to 1. And so this is going to be pi times 1/2 minus 1/5. And then what happens when I evaluate it at 0? God bless you. It wipes all those x's out, which is nice. And so then we're going to get a common denominator here, and we're going to get 5/10 minus 2/10. I'm foreshadowing the answer there. Minus 2/10, which is 3 pi over 10 units cubed, and you would be right. And for your viewing pleasure, I took GSP, or the Geometry Sketchpad program, and showed you what it would look like. So it's like a bowl, isn't it? Except that it's got, when you look in the bowl, it's kind of got a weird surface on the inside because it's going around. Pretty cool. All right, next. We're revolving now around the line. We're going to take the same area and revolve it about the line. Y equals -1. There it is. Y equals -1. That's our axis of revolution. And is this a disc or a washer? Yes, it's a huge washer. You're right. It's a washer. Okay, and since we're revolving it around a horizontal line, our rectangular piece of area that we're revolving is a dx. And so this is going to be ginormous. And remember, I apologized about how I draw these things. You don't have to draw them. If you can visualize it without drawing them, I'm just drawing them for illustrative purposes and to show you, what an incredible artist I am. Which is horrible. Okay, so this is going to have a really big center taken out of it, right? So now I have to figure out, though, what big R is. Well, big R is the radius of the outer disk, right? So it's going to be which function? Yes, because this is root x here. Y equals root x. It's going to be root x, because the distance from, I'm going to use blue, the distance from here to here is root x, isn't it? So what do I have to do to root x? I have to add this distance, which is 1. So big R is root x plus 1. And little r is going to be x squared plus 1. Everybody agree with that? So the formula is just big R squared minus little r squared with a pi in front of it. So it's going to be volume equals pi times the integral from 0 to 1 of big R, which is root x plus 1 quantity squared minus little r squared, which is x squared plus 1, all times dx. Now the only way to integrate this, sadly, is to multiply it all out. Okay, and since I'm running out of time, I'm not going to multiply it out, but I know that we could do that, and we can integrate that another time. So it's more important that I set it up. Because even with the AP exam, you get a point for the integrand, you get a point for the constant and the limit of integration. That's 2 points, right, so far? And then you get a point for the answer. So 2/3 of it is already set up. Yes, sir? Oh, yes, I have to put a square here. No, thank you for letting me know that. Yeah. Can't have my steer blown here. Very nice. Okay. All right, so set up another one. Because I want to be able to get to this one. This one we're revolving the same area about what now? The y-axis. Ooh, so we're revolving it around the y-axis. So now the area that I'm revolving has a rectangular shape that's thickness is now instead of dy or dx, it's dy. And this is also a washer. Now you're going to bear with me, right? Because this looks like a toilet seat. There's no doubt about it. It looks like a toilet seat, and we're just going to have to roll with it, okay? There it is. Here's our lovely toilet seat. But it's a washer toilet seat, right? You're never going to look at a toilet seat ever again quite the same way, are you? Okay. Anyway, so the volume's going to be pi times the integral. Now, this is going to be a dy here. So I have to have an integrand full of y's. Okay, but I have a function here that's y equals x squared, and I have one that's y equals the square root of x. So how do I fix that? I got to get them as x equals. So this is x equal root y. Now the plus or minus, some people might think about, but the plus root y is this one. The minus root y would be on the other side, okay? What about this next one? This is going to be x equals y squared. Good. All right, now we have to figure out what big R is. Well, big R is this distance, and little r is this distance. So big R is root y, yes. Everybody agree? And little r is y squared. Now this is going to set up an integral that looks just like the other one, but with respect to y, but I wanted to show you the difference. Okay, so that's going to be, I'll try to square both things this time, root y quantity squared minus y squared squared. And the y's are going from 0 to 1. Okay? So what is the difference between revolving around a horizontal line and a vertical line? With respect to dy, yes, is vertical. Now it makes sense, right? Because you're revolving around a y. Get it? dy. And you have to have an in-rand full of y's. So you have to have these as x equals. All right, let's set up the next one. We're revolving it around the line x equals -1. Same area. Now this is what kind of a line? It's vertical, so it's going to be with respect to y. So it's dy. And this one is another big washer. And I'm not going to draw it because it would be off the page. Are you okay with that? So what's big R in this case? I'm speeding up. I'm sorry, but we're running out of time. This is big R, and this would be little r. So what is big R functionally? Well, remember we said that this was x equals root y, and this was x equal y squared. So big R is root y, yes. And little r is y squared plus 1, which should look very familiar. So the volume is going to be pi times the integral from 0 to 1 of big R squared, which is root y, plus 1 quantity squared, minus y squared plus 1 quantity squared. There, I remembered to square that, dy. So we have to be on a mission to find big R and little r, right, functionally? And I always draw, as you see this, so I can see it, because visually that helps me. All right, 2 minutes. Can we do it? Yes, we can. This one, I'm just going to probably be able to set it up. This one, I'm going to revolve this area here that's between these curves and the y-axis, and I'm going to revolve it about the y-axis here. This is a combo. You get a disc and a washer for the price of one. Where's it a disc? From here to here, right from 0 to 1. You see how it's a disc? Because all of the area is adjacent, right? And then where's it a washer? Above it. Do you see how this is different? Bigger toilet seat. I have been known to tweet nice drawings of washers. Okay, so the volume is going to be a combination, so I'm going to hurry up here. And I have to have this function, which is y equals x squared plus 1 as a function of y. X is a function of y. So this is going to be y minus 1 equals x squared, right? So x equals the square root of y minus 1. I don't have to worry about the plus or minus. Okay, so I have 2. What's r here? This is r. From 0 to 1, what is r? It's just 1. So the first integral is going to be volume equals pi times the integral from 0 to 1 of 1 squared dy, right? Because we're squaring 1. Because these are both dy's. Plus, plus pi times the integral from 1 to 2 of well, what is big R here? Big R is from 1 to 2, big R is just 1, isn't it? So big R here is 1, and little r is this distance, which is root y minus 1. Okay, so it's going to be pi times big R squared, which is 1 squared, minus root y minus 1 quantity squared dy. And so I now have the disk part, and I have the washer part, and then we add them together and we get a disk washer. No. A disk washer? No, it's funny. That's funny. A little bit funny. Okay? And then, of course, we would have to integrate that to get what the actual answer is. Okay? So you might have problems where there are a combination. Okay? So the homework is from the book, just a couple of problems, and then from the area volume packet, it's going to be like the part B's. You know, because for part A is for the homework from last time for the areas. So the part B's and maybe a C from time to time about revolving that area about something, okay? Any questions? That was a little bit fun. A little bit different. All right. Well, thank you. Go to 2020. You rock, right?